This is the presentation for ME4056, Block 4, Group 4, the refrigeration cycle. So this presentation will start off with some background and goals for the experiment, move into the assumptions that are made for the project, and discuss the results for the data that has already been collected, and then finally move into the conclusion of what we expect to happen during a transient analysis. Some background information of a refrigeration cycle is that we're using a reverse Brayton cycle. This cycle uses a motor to power an air compressor, which increases the pressure and temperature of the air. This air is forced into an air-to-air heat exchanger, which is followed by an accumulator. The accumulator is necessary in order to maintain the pressure, and the heat exchanger removes the heat from the air without lowering the pressure. This high pressure air is then forced into a vortex tube, which acts as a turbine. The vortex tube will separate the compressed air into hot and cold components, each having their own respective mass flow rates. A vortex tube is a mechanical device that has no moving parts. And then this diagram here is a more in-depth schematic of the actual system that is going to be used. The goals for this analysis are to provide an accurate review of the cooling system that has been developed by Machine Chiller Incorporated. A characterization between the input voltage and the input pressure into the vortex tube will be found. This input pressure will then be analyzed in respect to the cold and hot outlet temperatures and the cold and hot mass flow rates. Additionally, the relationship between the temperature of the load and the input voltage will be determined. Utilizing these relationships, the actual thermal resistance of the insulation will be found alongside the material properties of the aluminum block. Lastly, the uncertainties will be calculated to justify whether the modeled system will accurately represent a true cooling system. To calculate the offsets that are built into the sensors, the temperatures and pressures are taken at a room temperature of 22 degrees Celsius and an atmospheric pressure of 99,000 pascals. The difference between these values and the values found at zero pressure will be used with the data that is not at zero PA. Additional assumptions that are made are that the pressure drop across the flow meters is negligible and that at steady state, the energy change on the load is assumed to be zero. This allows for the energy of the air to be found.
For the characterization of the data we found, at steady state, we took the average of all the values, and for the pressure values versus the input values of the voltage, this is the graph we found. As you can see, as you increase the input voltage of the compressor, the pressure does not fit this linear trend very well and appears to max out somewhere around 60,000 pascals. For the T4 cold and T4 hot, as you increase the input pressure of the system, the T4 cold system of the system does not follow the linear trend as well and appears to bottom out somewhere around 275 Kelvin, while the T4 hot does increase linear with the system. So as you increase the pressure, it will just keep on following that linear trend line. For the mass flow rates, for the M4 cold, this fits the linear trend line very well. So as you increase the pressure, you increase the mass flow rate of the cold part. But for the hot mass flow rate, the linear trend line does not fit this very well. So as you increase the pressure, it will steadily stop increasing over time. And the T load of the system does fit this linear trend line for this part of the range. However, looking at the last couple values, it looks like it's actually steadily decreasing in slope. So beyond the range, the linear trend line may not be as effective at describing the data.
So for our resistance results, they're characterized in the table here on the slide, but they were found by first finding the T5, T4 cold, T ambient, T load, and mass flow rate, along with the constant specific heat, combining those to find the ambient heat transfer, and then solving for the resistance using the ambient heat transfer, ambient temperature, and load temperature. The results are again characterized in the table. They range from about 4.8 to 10.2 Kelvin times second per joule, and they increase as the input voltage does as well. The theoretical value calculated using the geometry and thermal conductivity of the load block was found to be about 14.61 Kelvin times second per joule, meaning that our experimental results differ from the theoretical value by a significant amount. For the uncertainty analysis for the resistance, the total uncertainty analysis was found using the T4, T5, T load, as well as the measured mass flow rate of the cold air outlet, and then combining those with the uncertainty of the mass flow rate sensor, as well as the uncertainty of the thermocouples, and for data and the data acquisition uncertainty as well. Using this combined uncertainty was then added to the table of values, giving us uncertainty ranging from about 0.55 to 1.39, and somewhat increasing as our experimental resistance value increases, which was to be expected as the mass flow rate also increased. The sort of some takeaways from our values, from our experimental values, the theoretical and measured resistance values, they did not match very well, but they did improve and got closer with higher input voltages, but the theoretical resistance value was still outside of the uncertainty bounds. The increase in voltage also corresponded to an increase in cooling, meaning a decrease of the T load of the block, which was to be expected. This was all found, again, using the assumption of the ambient heat transfer is equal to the air heat transfer.
So during week 2, we'll move on to study the transient response of the system. This means data collection will begin before the system is pressurized. So starting from ambient temperature, the load will be cooled first with 40 psi, then 80 psi air. In between trials, the load will be heated back to ambient temperature to ensure the independence of each trial. We can then integrate the transient response with respect to time to calculate Q load, Q air, and Q ambient, which we will use in our load energy balance equation. Looking at our uncertainty analysis, we found that during the steady state response, the energy rate coming in from the surroundings should equal the energy rate going out to the cold air. We can compare the combined uncertainties of these terms to determine the validity of our modeling and sensing. This process will be repeated for transient analysis, where we'll compare the uncertainty of Q air against the uncertainty of Q load and Q ambient, which is shown here as Q total. Based on the results we've seen so far and those that we expect to see in the upcoming week, we intend on making the following conclusions. The system would work well for refrigeration applications, assuming rise time is not a concern. This is mostly evidenced by the load cooling by about 16 degrees Celsius in around 20 minutes. In general, increasing pressure improves system performance. There is a point of diminishing returns around 70 psi. Of pressure has minimal impact on the vortex tube output temperature. Future improvements to the system include increasing pressure, insulating the load to cover the entire surface area, increasing insulation depth, or using a better insulating material altogether.